Hello, my name is Jacqueline German. The title of my presentation is a review of rapidly exploring random tree path planning algorithms. First, I will go over the introduction and rapidly exploring random tree path planning algorithms. Then I will discuss the simulations and future work. This presentation will conclude with the acknowledgments and references. Path planning algorithms are autonomous robot navigation techniques that determine a robot's route to its destination. This diagram illustrates the different parts of a generalized path planning problem. The configuration space consists of free space and the obstacle space. The free space consists of everywhere that a robot can move, while the obstacle space consists of everywhere this robot cannot move. As can be seen from the diagram, the free space and the obstacle space are complements of each other. In addition, this robot's starting position is Q0 and its goal configuration is QG. The robot determines a path from QO to QG through the free space without touching the obstacle space. Combinatorial methods are path planning techniques that build structures in the configuration space that completely and discretely obtain all of the necessary data to plan a path. Combinatorial methods quickly converge to a solution. However, these methods are very complex because of the difficulty associated with dividing the configuration space into polygons. Consequently, they are difficult to implement. Types of combinatorial methods include visibility graphs, cell decomposition techniques, including exact cell decomposition and approximate cell decomposition, and Voronoi diagrams. A visibility graph is a network of intervisible locations, and the figure on the right shows an example of a visibility graph. Visibility graphs consist of vertices and edges. Vertices include corners of obstacles and the initial and goal configurations. The edges include collision-free connections between the vertices. Exact cellular decomposition methods include trapezoidal and triangular decomposition. For trapezoidal decomposition, the first step is to obtain a 2D polygonal region and place the initial and goal configurations in the free space. Next, the free space is divided into trapezoids. Also, place vertices on every vertical line and inside of each trapezoid. Then, connect the vertices to their nearest neighbors. Lastly, search for the shortest path from the start to goal configurations. In addition, triangular decomposition has the same procedure as trapezoidal decomposition, except it divides the free space into triangles instead of trapezoids. Approximate cell decomposition techniques model the environment as an occupancy grid map, which consists of square-shaped cells. The figure on the right is an example of an occupancy grid map. The cells are either occupied or unoccupied. Cells that mostly contain obstacles are occupied, while cells in the free space are unoccupied. The graph is then constructed using cell vertices as corners and connections between them as edges. Lastly, a graph search method is employed to determine a path from the initial to the goal configurations. In a Voronoi diagram, all of the points have the same clearance from obstacles, and the figure on the right shows an example of a Voronoi diagram. The advantage of this method is that it ensures that robots maintain a safe distance from obstacles. The disadvantage is that the affinity for open spaces may cause the path to be longer than if it remains closer to obstacles. Now, sampling-based methods employ collision detections to repeatedly probe the configuration space for a path. Sampling-based methods are much easier to implement and combinatorial methods because sampling-based methods do not divide the configuration space into polygons. Consequently, sampling-based methods are used for industrial-grade problems. However, sampling-based methods have longer convergence times than combinatorial methods. The two types of sampling-based methods are probabilistic roadmap and rapidly exploring random tree algorithms. The probabilistic roadmap algorithm is an example of a sampling-based technique. The figure on the right illustrates the process of constructing a probabilistic roadmap. The first step is to sample random points in the configuration space. The points in the free space are saved as milestones, while the points in the obstacle space are ignored because the robot cannot travel to these locations. The initial and goal configurations are also added to the milestone list. Next, connect each milestone to its nearest neighbors. The collision-free connections are saved as local paths. Lastly, the probabilistic roadmap is searched for a path from the start to the goal configurations. Now I will discuss three types of rapidly exploring random tree algorithms, including the rapidly exploring random tree, rapidly exploring random tree star, and informed rapidly exploring random tree star algorithms. The rapidly exploring random tree algorithm is a sampling-based method that determines the path from the start to goal configurations. To do so, it constructs a search tree that consists of vertices and edges. The advantage of this method is that it's simple to implement. However, the paths generated by this technique are not optimized because this algorithm terminates as soon as it finds a solution. This table shows the pseudocode for the RRT algorithm. It begins by automatically adding the initial and goal configurations to the vertices list. It then selects a random point in the configuration space. If the random point is in the free space, the nearest point in the tree to the random point is calculated. Next, this algorithm attempts to draw a line from the nearest point to the random point. If this line is collision-free, the random point and the nearest point are added to the search tree, and a line is extended between the 2 points. This algorithm terminates when the goal is reached. It outputs the search tree and the completed path. The rapidly exploring random tree star algorithm is an optimized version of the RRT algorithm. It incorporates near-neighbor search and rewiring tree functions. The advantage of this algorithm is that it reduces the distance that a robot travels. However, this method may have a longer convergence time than the RRT algorithm because this method continues to select random points to optimize the path until the number of iterations set by the user is reached. This table provides the pseudocode for the RRT star algorithm. It shows that the inner loop of the RRT pseudocode has been modified by adding near, choose parent, insert node, and rewire functions. The informed rapidly exploring random tree star algorithm improves upon the RRT star algorithm because it searches an ellipse with foci located at the start and goal configurations. The figure on the right shows the search ellipse. The minimum distance between the start and goal configurations is Cmin. The advantage of this method is that it reduces the size of the search area to the elliptical area in close proximity to the start and goal configurations. Because the search trees only include points nearby to the start and goal, the generated routes are much shorter. This table provides the pseudocode for the informed RRT star algorithm. It shows that the RRT star pseudocode had been modified to sample an elliptical search area. Now I will discuss the simulations. The objective of these simulations is to compare the performance of the RRT, RRT star, and informed RRT star algorithms for two simulated environments. The runtime, number of searches, number of nodes in the tree, number of nodes in the final path, and path length were measured. The Python robotics toolbox was used to conduct these simulations. The maximum number of iterations for each path planning algorithm was set to 200. In addition, the search area is two-dimensional. The x and y coordinates of the search area range from -2 to 15 to give the search tree extra room to reach the goal configurations from different directions. In addition, the search area contains circular obstacles. The initial configuration is placed at 0, 0, and the goal configuration is placed at 10, 10. These tables contain Obstacle List 1 and Obstacle List 2. Obstacle List 1 was used for the first set of simulations. This obstacle list consists of 8 circular obstacles, which formed an L-shaped wall. This obstacle set was selected to see if the path planning algorithms could navigate around the wall to reach the goal configuration. Likewise, the obstacle set 2 was used for the second set of simulations. This obstacle set contains 6 obstacles which form a wall with narrow gaps between the obstacles. Obstacle set 2 was selected to see if the path planning algorithms could navigate through a narrow gap in the wall to reach the goal configuration. These diagrams show the simulations corresponding to obstacle set 1. Figures A and B correspond to trial 2 for the RRT simulation. Figure A shows the search tree. The total number of searches to construct this tree is 51. The total number of nodes in the tree is 30. Figure B shows the final path for this simulation. There are 11 nodes in this path, and the path length is 25.04. Figures C and D correspond to trial 9 of the RRT star algorithm simulation. Figure C shows the search tree. The total number of searches to construct this tree is 200, because that is the maximum number of iterations. The number of nodes in the tree is 154. Figure D shows the final path for the simulation. There are 5 nodes in this path, and the path length is 18.94. Figures E and F correspond to trial 8 for the informed RRT star algorithm. The total number of searches is 200, because this is the number of iterations. The number of nodes in the tree is 115. Figure E shows the final path for the simulation. There are 6 nodes in the path, and the path length is 18.18. These diagrams show simulations corresponding to obstacle set 2. Figures A and B correspond to trial 5 for the RRT simulation. Figure A shows the search tree. The total number of searches to construct this tree is 24. The total number of nodes in this tree is 21. Figure B shows the final path for the simulation. There are 11 nodes in this path, and the path length is 19.44. Figures C and D correspond to trial 2 for the RRT star simulation. Figure C shows the search tree. The total number of searches is 200, which is the number of iterations. The number of nodes in this tree is 191. In addition, Figure D shows the search path for this trial. There are 5 nodes in this path, and the path length is 14.69. Figures E and F correspond to trial 29 for the informed RRT star simulation. Figure E shows that the foci of the search ellipse are the start and goal configurations. The total number of searches is 200, and the number of nodes in the search tree is 182. In addition, Figure F shows the final path generated by the informed RRT star algorithm. There are 4 nodes in this path, and the path length is 14.29. The path length was determined by calculating the distance between each consecutive pair of points. To calculate the change in position from the current point in the path to the next point in the path, subtract the x and y coordinates of the current point from the x and y coordinates of the next point. The change in position along the x-axis and the change in position along the y-axis are squared and added together. The distance from the current point to the next point is found by taking the square root of this quantity. To calculate the total path length, add the distances between each consecutive pairs of points together. Each simulation was repeated for at least 30 trials or until a path could be found 30 times. The mean and the standard deviation were calculated for each quantity. The first equation is the formula for the mean, while the second equation is the formula for the standard deviation. For the first obstacle set, the runtimes for the RRT, RRT star, and Informed RRT star algorithms were 0.51 seconds, 0.47 seconds, and 0.54 seconds, with standard deviations of 0.26 seconds, 0.26 seconds, and 0.31 seconds respectively. For the second obstacle set, the runtimes were 0.53 seconds, 0.45 seconds, 0.47 seconds. The standard deviations were 0.3 seconds, 0.23 seconds, and 0.24 seconds respectively. Algorithms with shorter runtimes are more efficient than those with longer runtimes. For the RRT algorithm, the mean number of searches was 42.63 with a standard deviation of 25.88. For obstacle set 2, the mean number of searches was 20.87 with a standard deviation of 9.48. The mean number of searches is higher for obstacle list 1 because a larger portion of the search area is taken up by obstacles. For the RRT star and Informed RRT star algorithms, the mean number of searches is equal to 200 because these algorithms continue to select random points in the search tree to improve the path until the maximum number of iterations is reached. For the first obstacle set, the mean number of nodes in the search tree were 24.73, 149, and 111.99, with standard deviations of 16.52, 11.41, and 15.95 respectively. For obstacle list 2, the mean number of nodes in the search tree were 15.33, 183.60, and 171.75 with standard deviations of 8.32, 4.23, and 13.38 respectively. The number of nodes in the search trees constructed by the RRT algorithm is much lower than the number of nodes in the search trees constructed by the RRT star and Informed RRT star algorithms. This is because the RRT algorithm terminates as soon as it finds a path to the goal configuration instead of continuing to sample the environment to optimize the path. For the Informed RRT star algorithm, the number of nodes in the search tree for obstacle list 1 is much less than the number of nodes for obstacle list 2. For the first obstacle list simulations, the L-shaped wall took up most of the space in the search ellipse. Consequently, a lot of the randomly selected points were not added to the tree because these points would have caused collisions with obstacles. For obstacle list 1, the mean number of nodes in the path for the RRT, RRT star, and Informed RRT star algorithms were 9.97, 4.87, and 6.20 with standard deviations of 1.19, 0.43, and 0.85 respectively. For obstacle set 2, the mean number of nodes in the path for the RRT, RRT star, and Informed RRT star algorithms were 8.20, 4.23, and 4.60 with standard deviations of 1.49, 0.43, and 0.67 respectively. The Informed RRT star algorithm had more nodes in the path than the RRT star algorithm because the Informed RRT star algorithm made sharper turns around the obstacles. For obstacle set 1, the mean path lengths were 23.76, 19.07, and 18.19 with standard deviations of 2.93, 0.57, and 0.25 respectively. For obstacle list 2, the mean path lengths were 19.60, 14.59, and 14.28 with standard deviations of 3.07, 0.37, and 0.15 respectively. Consequently, the Informed RRT star algorithm found the shortest path for both obstacle sets. The RRT and RRT star algorithms had 100% success rates for both obstacle sets. However, the success rate for the Informed RRT star algorithm was 14.67% for the first obstacle set and 94% for the second obstacle set. Therefore, the success rate of each path planning algorithm depends on the arrangement of obstacles in the environment. Future experiments involve implementing and repeating the simulations with the variable step size RRT algorithm, which adapts the distance the search tree extends based on the proximity of obstacles. In addition, 3D versions of the RRT, RRT star, and Informed RRT star algorithms could be implemented so that they could be applied to robots such as unmanned aerial vehicles. To conduct these simulations, spherical landmarks would be created. The distance calculations in each path planning algorithm will also be modified to include X, Y, and Z coordinates. A hearty thank you to the FAMU FSU Dean's Engineering Fellows Program and to the Department of Electrical and Computer Engineering for their support with this project. These are the references that were used for this presentation. That's all for my presentation. Thank you very much for your attention.